أهلا وسهلا. Lecture 28 is going to be another tutorial where we're going to solve or at least discuss a couple of problems. The first problem is actually very nice, talking about an irreversible isothermal gas phase reaction where it is carried out in a packed bed reactor. So that means you have a pressure drop. So let's look. A and B enters into the reactor with a pressure of 10 atmosphere, and when it exits at a pressure of only 2 atmosphere after going through 100 kg of catalyst, of packed catalyst. Okay, so it's a very nice problem. I will just tell you where the students make mistake, and so you can avoid it. Okay, so the problem is when you write actually concentration of A, which is Fa divided by epsilon, and of course inside epsilon here you have P naught over P, correct? So you will end up using Y into the concentration problem, the concentration equation. Students tend to choose Y equals 2 divided by 10, which is 0.2, which is wrong, right? Y does not equal 0.2. Y equals 0.2 at the exit only, but through the bed of the reactor, Y equals P over P naught, and P in fact is variable, right? So P varies between 10 atmosphere and drops down as it goes down the length of the reactor until it reaches 2 atmosphere at the exit. So Y is variable, it's not a constant in this equation. However, you can use the value of Y equal 0.2 at the exit, where W equals to 100 kg, to find the value of alpha, correct? So that's how you're gonna utilize this information. Okay, and of course there are other requirements as well. But let's go to problem 410. Problem 410, it's actually a lengthy problem, but you have all the time to solve it at home. I'm not going to read the statement. I'm just going to summarize what you need to do here. Okay, how X changes with the particle size. That's the topic of problem 420. The elementary gas phase reaction A plus B goes to C plus D is carried out in a packed bed reactor. Currently, catalyst particles 1 millimeter in diameter are packed into the reactor. It is suggested that X could be increased by changing the catalyst particle diameter. So by changing dP, we could increase X. Use the given data to correlate the specific reaction rate K prime as a function of dP. Remember we said K, or in this case it's an overall rate constant, is function of dP. So it's affected by dP, right? Then use this correlation to determine the catalyst size that gives the highest conversion. Flow is turbulent throughout the bed. There are some typos in the units and values of the given parameters, and this is concerning alpha naught. When we say alpha naught, basically we mean alpha at the reference state, okay, or the reference condition, or the initial condition, the one which is given. Okay, and then you have rho B, the bulk density, which is 1.5 kg per liter, and then you have C at 75 millimeter inverse. So if you have different values in your textbook, make sure you correct them according to these corrected values. So let's see what we have. it's given that K prime, the overall rate constant, equals eta times K. Eta times K. What is eta? Eta is the internal effectiveness factor. The internal effectiveness factor. Okay, what about eta? What does it equal? Eta equals 3 over phi square times phi cotangent hyperbolic phi minus 1. And what is phi? Phi is c times dp. So what is phi? Basically, phi is the Thiele modulus. It's Thiele modulus. So we said eta is the internal effectiveness factor and phi is Thiele modulus. Okay, so let's see. Let's have some more information about the situation. We said the flow is turbulent, so we can assume that the external diffusion limitation is negligible, or the external mass transfer resistance is negligible. That is the diffusion through the boundary layer outside the particle size, outside the catalyst size, catalyst particle. In other words, we're assuming we don't have to worry about the external mass transfer. We don't have to worry about the external diffusion. So we only worry about the internal diffusion. So basically, Ca at the bulk equals the Ca on the surface of the particle size. So we only have to worry about how the concentration varies inside the particle size. So inside the particle at the active site, the concentration is not really the same as the concentration in the bulk. So we have some internal diffusion limitation. That's why we have the internal effectiveness factor. If the internal effectiveness factor was 1, that means, woo, perfect. It's just diffusing like there is no resistance, correct? Otherwise, if it's less than that, that means we have some internal diffusion limitations. What about Thiele modulus? Well, you are already familiar with Thiele, right? McCabe Thiele. Okay, that's in separation course. Okay, he's the same gentleman. Okay, so let's learn more. The eta, or the internal effectiveness factor, is a measure of the relative importance of diffusion and reaction limitations. And it equals, or is defined as, the actual overall rate of reaction. That's the overall rate of reaction that you observe. Okay, so it's the actual overall rate of reaction, or the observed overall rate of reaction, divided by the rate of reaction if entire internal surfaces were exposed to CAS and TS. Okay, so obviously, if the internal diffusion, you did not have a problem with it, the internal diffusion was so fast, therefore, the concentration inside the particles would be the same as the concentration on the surface of the particle. Therefore, eta will equal to 1, given that, of course, the temperature is the same inside and outside the particle. Okay, however, in reality, that's not the case. The concentration inside the particle, which affects the overall rate of reaction, is less. Therefore, you will end up with less overall rate of reaction compared to the ideal case, where the rate of reaction equals to that, or calculated based on the assumption that the concentration inside the particle is the same as the concentration at the surface. Okay, and in this case, of course, since the numerator is smaller than the denominator, the value of eta will be less than 1. Okay, so it can be written as eta equals minus Ra prime, this is the overall rate of reaction, divided by minus Ra prime S, meaning the rate of reaction at the surface. type. The subscript S indicates that the rate minus RAS is evaluated at the conditions present at the external surface of the pellet. Type. So we said K prime equals eta times K, and we know what the equation of eta is. It's given, tamam, and eta is the internal effectiveness factor. Let's talk about phi. Phi. Here the phi is written capital. Of course, it's written capital in this chapter because we want to distinguish it, distinguish between this phi and the phi which we know about, which is the void fraction, which is the small letter phi. But in fact, the Thiele modulus is always written as a small letter phi with a subscript n, where n is the order of the reaction. Okay, so we said phi or phi n is the Thiele modulus, where n is the reaction order. What about phi square? Phi square is a measure of the ratio of a surface reaction rate to a rate of diffusion through the catalyst pellet. So it's a comparison between two different rates. So you're comparing the surface reaction rate, so it's the rate of reaction at the surface, you're comparing it to the diffusion rate. What does large phi imply? So if you have large phi, that means that the surface reaction rate is way faster than the diffusion rate, correct? So what does that mean? If the surface reaction rate is very fast compared to the diffusion rate, that means the diffusion rate is very slow, right? So the reaction is limited by the internal diffusion, correct? So when the Thiele modulus phi is large, internal diffusion usually limits the overall rate of reaction. And when phi n is small, that means the surface reaction rate is smaller or slower compared to the diffusion rate. Diffusion rate is fast. I don't have problem with the diffusion. I have problem with the reaction rate. So in this case, the surface reaction is usually the rate limiting. Okay, so what do we need to do at the beginning? We need to show the following. We need to show that alpha naught equals 0.8 times 10 to the power negative 4 per kg, right? So how you gonna get alpha? Where are you gonna get alpha from? Again, the naught here means the initial case where the particle size is given. Okay, it's the reference case. Okay, obviously you get alpha naught from beta naught, and beta naught in this question is given. Otherwise, if it was not given, you know how to calculate beta naught, right? You know how to calculate beta naught. Okay, and then you need to find an equation for alpha as a function of the particle size. How alpha changes as the particle size changes. Of course, you know that as the particle size increases, right, the alpha value decreases, means the flow will experience less pressure drop. How are you going to get this relationship? Oops, you will get it from, of course, the definition of beta naught, and how beta naught is function of dP, and then you will look at alpha, right, and see how alpha is function of beta naught. Type. What else? You need to show that C equals 75 millimeter inverse. That's something you need to show. How are you going to do this? You're going to use the Thiele modulus definition, which is given as C, which is a constant, times the particle size, the catalyst particle size. Okay, so let's elaborate on the last requirement, that is C equals 75 millimeter inverse. You have to show this. So how are we going to show this? Okay, first we know that K prime equals eta times K, and we know what eta equals. We have an equation for eta. Right, let's go and see this plot which we are familiar with. That is the overall rate constant. The overall rate constant is function of the particle size function of the particle size according to this functionality. Okay, where at the very small particle size, the surface reaction sequence is the slow step. However, at very large particle size, the internal diffusion is the slowest step. So if the particle size was very small, that means the K prime, right, is mainly coming from the surface reaction sequence, right? Coming mainly from the surface reaction sequence, or we can say it's almost equal to the kinetic K, the K which is coming from kinetic only, from the rate constant, right? This K is coming as a result of kinetics, how fast the reaction goes, right? But this K is a result of 7 things, right? It's the external diffusion, internal diffusion, then the adsorption, then the surface, then the reaction, surface reaction, then the desorption, then the internal diffusion, and then the external diffusion, right? Okay, so when the particle size is very small, and in this case where we don't have external diffusion limitation, so the K prime actually represents the kinetic K. Okay, so let's plot with this data which is given in the problem. We have K prime versus dP is given, and طيب, so here we go. K prime versus dP, K prime versus dP coming from this table. And as you can see, I'm using a log scale, right? I'm using the log scale. And you can see the similarity between this figure and this figure. Okay, so we said at very small particle size, the K prime should equal the K. Is that true though? Let's see. We can also find that. Okay, so basically we are saying eta equals 1. That's what we are saying. So why don't you go ahead and calculate eta? Okay, anyway, so we have just showed that we can find the value of K, right? Because we have K prime, and we said at very small particle size the eta should be 1 and K prime equals K, so we have the value of K. طيب, let's see what we have at very large particle size. At very large particle size, phi is also very large, right? Very large particle size. That means phi is very large as well. So the quotidian hyperbolic would mathematically reduce to 1. The quotidian hyperbolic would mathematically reduce to 1. And then you have eta equals 3 over phi. Eta will equal 3 over phi. So you can utilize this value. Okay, and then you're gonna use it to find the value of C. Okay, and after finding the value of C, you can again, as we said, you can confirm that the value of eta equals 1 at very small particle. Okay, and then of course you're gonna solve the problem, and you will have now an equation where K, show this, where K prime is function of eta, and eta is function of phi, and phi is function of the particle size. So basically you have the overall rate constant is function of dp. You have this equation, and also you know that the pressure drop is also a function of particle size through Ergun equation and through the pressure drop parameters, right? Beta and alpha. Okay, so you're going to use all of these to set up your design algorithm and find the final solution here. Let's see, look at the final solution. Here we are plotting x, or the pressure drop, versus dp. Okay, so we're plotting x, or the pressure drop, versus dp, and we are also plotting k prime. Of course, we only need to plot x versus dp, but I'm also plotting the pressure drop and k prime to understand what's going on. So again, at very small particle size, we said k prime here, k prime, right, it's at maximum value, or it equals the k of the surface reaction sequence. Correct? Very large. So you expect x to be very large. However, at very small particle size, the pressure drop is very large, right? The pressure drop is very large. See, Shabab, the pressure drop is, what is the pressure drop here? That's the blue one. Is it blue? Yeah, kind of. Okay. Tiffany blue maybe, or maybe not. Maybe darker blue. Anyway, so at very small particle size, you can see that the pressure drop is very large, and therefore the conversion is not as large as it could be. Correct? It's not as large as it could be. Okay, let's look at very large particle size. At very large particle size, I have solved the problem of pressure drop. See, the pressure drop is less than 2%. Okay, the pressure drop is less than 2%. But the problem is with the k prime. The k prime is very small. Why k prime is very small? Because the internal diffusion faces large resistance, large limitations. Therefore, k prime becomes very small, and again, the conversion is very small. So at very large particle size, the conversion is very small. At very small particle size, the conversion is small. There is an optimum solution. Somewhere in the middle. Okay, so this is the optimum particle size where conversion is at maximum value. Okay, so with this we finish this problem. Please look at it carefully at home.